Hello, friend. Some nights the sky feels closer than it should. Stars lean in, silence hums. And if you look up long enough, you might notice something that shouldn't be there. A soft smudge of light barely visible hanging just above the horizon, like a whisper that forgot to fade. That light has been traveling for 2.5 million years. It left its home before humans knew fire, before we had words, before we understood that we were small. And tonight, it's finally reaching your eyes. What if the thing you're looking at isn't really there anymore? What if you're seeing a memory painted in photons drifting through the dark? That smudge has a name: Andromeda, our nearest galactic neighbor, a river of 1 trillion stars flowing silently toward us. Before we begin our quiet journey together, I want to thank you for being here. If you find comfort in these soft nights of science, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you. It means more than you know. Now, let's drift. Tonight we walk through light and time, through ancient myths and modern mysteries. We'll meet a galaxy that's been watching us longer than we've been watching it. A galaxy that holds 1 trillion suns, spins in near silence, and is quietly, steadily moving closer. You don't need to understand everything. Just rest here. Let your mind wander. And if you drift off halfway through, that's exactly where you're meant to be. Andromeda is not just a galaxy. It's a question written in starlight, a mirror held up to our own Milky Way. And maybe a glimpse of what's to come. Let's begin where all great stories begin, with someone looking up and wondering what that strange light could be. Thousands of years ago, long before telescopes, long before we knew what galaxies were, people saw it. A faint patch of glow in the autumn sky, soft and blurred, like a thumbprint left on glass. They had no word for it, no science to explain it, but they named it anyway. The Greeks called it Andromeda after a princess in their mythology, a woman chained to a rock, waiting to be devoured by a sea monster until a hero came to save her. It's a strange name for something so distant and serene. But perhaps they saw in that light what we still see now, something beautiful, something vulnerable, something caught between darkness and rescue. But the Greeks weren't the first. In Persia, the astronomer Abd al-Rahman al-Sufi wrote about it in the year 964. He called it the little cloud. He didn't know what it was. He just knew it was there, constant and quiet, like a stain on the night that wouldn't wash away. In China, ancient records called it the white cloud. In Arabia, the mysterious nebula. Every culture that looked up saw it, and every one of them wondered. For over 1,000 years, humans believed Andromeda was part of our own star system, just another nebula, a cloud of glowing gas somewhere inside the Milky Way. No one imagined it could be something bigger, something outside, another universe entirely. It wasn't until 1923 that the truth arrived quietly through the work of a man named Edwin Hubble. Using the largest telescope in the world at the time, Hubble measured the light of a single star inside that soft blur, and what he found changed everything. That star was too far away, much, much too far beyond the edges of our galaxy, far beyond anything anyone thought possible. Andromeda wasn't a cloud, it wasn't a nebula, it was a galaxy, an entire island of stars spinning in the dark 2.5 million light years away. Suddenly the universe was bigger, and we were smaller. It's strange to think how long it took us to see the truth, how many centuries we spent staring at something and getting it wrong. But maybe that's the lesson Andromeda teaches us first. Sometimes the things that are closest to us are the hardest to understand. Scientists suggest this happens because of the way our eyes work. We see patterns. We see what we expect to see. And when something is too large, too distant, too unlike anything we know, our brains try to fit it into something familiar. A cloud, a smudge, a mistake. It's as if, even in our looking, we're half blind. But here's the beautiful part: we kept looking anyway. Generation after generation, humans pointed at that little blur and asked, "What is that?" Even when we got the answer wrong, we kept asking. Even when the answer seemed impossible, we kept searching. And eventually, the light told us the truth. Andromeda is made of about 1 trillion stars. That's more stars than there are grains of sand on all the beaches of Earth. Each one of those stars is a sun burning quietly in the dark, and many of them scientists believe likely have planets, worlds, maybe even life. But here's what makes Andromeda even stranger. It's bigger than the Milky Way, wider, brighter, and yet, when you measure its mass, it's almost the same as ours. How can something larger weigh the same? The answer lies in what we can't see: dark matter. An invisible ocean that fills the space between stars, holding everything together with gravity we can measure but cannot touch. We'll return to that mystery later. For now, just know this. Most of what Andromeda is made of, we cannot see. Most of what anything is made of, we cannot see. When you look at Andromeda with your naked eye, you're seeing only a fraction of what's really there. You're seeing light from the brightest stars, the hottest cores, the loudest parts of a galaxy that hums mostly in silence. The rest is shadow. The rest is weight without form. And still that small smudge you see is breathtaking because it contains everything: birth and death, explosions and stillness, 1 trillion quiet fires burning across a span of space so large it would take light itself 220,000 years to cross from one edge to the other. When ancient humans saw that blur, they didn't know any of this. They didn't know about galaxies or light years or dark matter, but maybe they felt it. Maybe something in them recognized that they were looking at something vast, something ancient, something that had been there long before them and would be there long after. Maybe that's why they gave it a name, not to explain it, just to remember it. The name stuck. And now, when astronomers talk about our nearest galactic neighbor, they still call it Andromeda, a princess chained in myth, glowing softly in the autumn sky. But Andromeda is not waiting to be saved. It's moving, drifting through space at 110 kilometers per second. And it's coming toward us, not away, toward. While the rest of the universe expands, while distant galaxies flee from us in every direction, Andromeda is falling closer. Scientists call this a blue shift. The light from Andromeda is compressed as it moves toward us, shifting slightly toward the blue end of the spectrum. It's the cosmic equivalent of a siren growing louder as it approaches. In 4.5 billion years, Andromeda will collide with the Milky Way. The two galaxies will pass through each other, stars scattering like pollen in a breeze, and then fall back together again, merging into something new. Something neither of us will be around to see, but we can imagine it. We can picture the sky filled with light, the heavens crowded with unfamiliar stars, the night no longer dark, but glowing softly with the breath of two galaxies becoming one. For now, though, Andromeda is still just a whisper, a small patch of light, a question we're still learning to answer. And maybe that's enough. Maybe it's okay not to understand everything, to just look up and feel the pull of something larger, something older, something that's been watching us all along. Because when you see Andromeda, you're not just seeing stars, you're seeing time. You're seeing light that began its journey before humans learned to speak, before we built cities, before we even knew we were lonely in the dark. That light has crossed an ocean of space to reach you. And tonight, it finally has. So, take a breath. Let the world go quiet. And know that somewhere out there, a river of stars is flowing toward us, slow and steady and unstoppable. Have you ever looked up and seen it? That soft smudge of light just barely there. If you have, you've already touched something ancient. If you haven't, maybe tonight's the night. And as we move forward, we'll drift deeper into the story of this silent river, into the myths that named it, the science that revealed it, and the slow, inevitable dance that will one day make it ours. But first, let's talk about the people who saw it before science had words for what it was. Long before we had the word galaxy, We had stories. Long before we understood light years, we understood longing. And long before anyone knew what Andromeda truly was, people looked up at that pale smudge in the autumn sky and felt something stir inside them. They gave it names, not scientific names, human names. Names born from wonder, confusion, and the deep need to make sense of the night. The story begins in ancient Greece around the year 150 CE, when a man named Ptolemy recorded the position of what he called a nebulous star in the constellation of Andromeda. He didn't know what it was, he just knew it was there, faint and unchanging, like a thumbprint pressed into the dark. But the name itself, Andromeda, comes from something older, a myth. A princess chained to a rock by the sea sacrificed to appease a monster, saved at the last moment by a hero riding a winged horse. It's a story of helplessness and rescue, of beauty and terror, of something precious offered up to the dark. Why did they name a patch of light after a story like that? Maybe because the light looked fragile, or maybe because they sensed somehow that it was caught between forces they couldn't see, chained by gravity, waiting in the silence. The Greeks weren't the only ones watching. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi documented that same blur of light in his book of fixed stars. He called it the little cloud. He described it as a small cloud that could be seen on clear moonless nights hovering near the stars that form the constellation. Al-Sufi didn't have a telescope. He didn't have photographs. He just had his eyes the desert sky and an insistence on writing down what he saw. And what he saw was something that didn't fit, something that wasn't quite a star, but wasn't quite empty space either. For centuries, no one knew what to do with that observation. It just sat there in the records, unexplained and patient, waiting for someone to figure it out. In China, astronomers had their own name for it. They called it the white cloud. In their star maps, it appeared as a faint glowing patch near the northern horizon in autumn. They tracked it carefully, noting its position, its constancy, its refusal to move like a comet or fade like a meteor. But they didn't call it a separate world. No one did. The idea that something could exist outside our own star system, outside our cosmic neighborhood entirely, was unthinkable. The universe, as far as anyone knew, was small, contained, ours. For over 1,000 years, astronomers across the world looked at Andromeda and made the same mistake. They thought it was close. They thought it was part of the Milky Way. A cloud of glowing gas, maybe. A cluster of unresolved stars. Something nearby, something familiar, something that belonged to us. Even when the first telescopes appeared in the 1600s, the confusion continued. Astronomers like Charles Messier cataloged these fuzzy patches of light, calling them nebulae, the Latin word for clouds. Messier's catalog, published in 1774, listed Andromeda as object number 31. M31, a cloud, nothing more. No one imagined it could be something vast. No one thought to ask, what if it's not close at all? What if it's impossibly far away? It wasn't until the early 1900s that the question finally cracked open, and when it did, the universe changed forever. In 1920, a debate took place at the Smithsonian Museum of Natural History in Washington, D.C. It's now known as the Great Debate. Two astronomers stood on opposite sides of a single question. Are these spiral nebulae part of our galaxy, or are they separate galaxies entirely? One astronomer, Harlow Shapley, argued they were inside the Milky Way. The other, Haber Curtis, argued they were island universes, distant galaxies far beyond our own. Neither could prove it, not yet. The tools didn't exist. The measurements were too uncertain. So the debate ended without a winner, and the question hung in the air like smoke. But 3 years later, in 1923, a young astronomer named Edwin Hubble looked through the newly completed Hooker telescope at Mount Wilson Observatory in California, the most powerful telescope on Earth at the time. He pointed it at Andromeda, and he found something no one expected: a single star, not a cloud, not a blur, a star. A type of star called a Cepheid variable, which pulses in brightness in a predictable rhythm. And because astronomers had already figured out how to use that rhythm to measure distance, Hubble could calculate how far away that star was. The answer was staggering. That star was nearly 1,000,000 light years away, far, far beyond the edges of the Milky Way, far beyond anything anyone had dared to imagine. Andromeda wasn't a nebula, it wasn't a cloud, it was a galaxy, an entire universe of stars spinning quietly on the other side of an ocean of space. When Hubble published his findings, the cosmos doubled in size overnight. And then it kept growing. Because if Andromeda was a separate galaxy, then so were all the other spiral nebulae scattered across the sky. The universe wasn't just bigger than we thought, it was unimaginably, incomprehensibly larger. And we were smaller than we'd ever been. It's humbling to think how long it took us to see the truth. For over 2,000 years, humans stared at Andromeda and got it wrong. Generation after generation of astronomers, philosophers, and sky watchers looked at that soft glow and called it something it wasn't. But maybe that's not failure. Maybe that's just the way understanding works. Slowly, in layers. With each generation adding one small piece to a puzzle they'll never finish. Scientists suggest this happens because of the limits of human perception. Our eyes evolved to see what's useful for survival. Predators' food faces in the firelight. They weren't built to comprehend distances measured in millions of light years. They weren't designed to grasp the scale of galaxies, so when we look at something too large, too distant, too unlike anything in our everyday experience, our brains do what they always do. They simplify. They find the closest match. A cloud, a smudge, a mistake. It's as if our minds are built for the small and near, and the vast and far slips through our fingers like water. But here's the beautiful part: we kept trying anyway. Even when the answers seemed impossible, even when the tools didn't exist. Yet, even when the truth was too large to hold, we kept asking. We kept looking. We kept writing it down, passing it forward, hoping that someday someone would understand. And someone did. Eventually, quietly. Through a telescope on a mountain in California, in the middle of the night, when the world was asleep, and the stars were finally still enough to be measured. That's how most truths arrive. Not with thunder, just with light and patience and someone willing to look a little closer than everyone else. The lesson Andromeda teaches us here is simple. Sometimes the things closest to us are the hardest to see. Not because they're hidden, but because they're too big, too strange, too far outside the boundaries of what we thought was possible. How many other things are we looking at right now and getting wrong? How many mysteries are sitting in plain sight, waiting for someone to ask the right question? The ancient Greeks saw a princess chained to a rock. The Persians saw a little cloud. The Chinese saw a white smudge in the northern sky. And for over 1,000 years, all of them were right and all of them were wrong. Because Andromeda was never a cloud. It was never a myth. It was always a galaxy. A river of 1 trillion stars spinning in the dark, waiting for us to understand. And when we finally did, the universe opened up like a door we didn't know was there. Now we know Andromeda is about 2.5 million light years away. We know it's roughly 220,000 light years across. We know it contains about 1 trillion stars, more than twice as many as the Milky Way. We know it has a supermassive black hole at its center, satellite galaxies orbiting around it, and spiral arms that curve through space like frozen waves. But knowing all of that doesn't erase the original mystery, it just deepens it. Because now the question isn't, what is that light? The question is, how did we ever think it was anything else? And maybe the answer is this: we see what we're ready to see, no sooner, no later. Just when the light finally reaches us and we finally have eyes capable of receiving it. For 2,000 years, Andromeda was a story, a cloud, a myth. And then in 1923, it became something else, something real, something vast, something that made us smaller and the universe infinitely larger. But the light itself never changed. It just kept traveling, kept glowing, kept waiting for us to catch up. Have you ever gotten something so completely wrong that when you finally learned the truth, it felt like waking up? That's what Andromeda gave us, a wake-up call written in starlight. And as we drift forward, we'll start to see what Andromeda is made of. Not the myth, not the name, but the actual physical beautiful truth of a trillion suns spinning silently in the dark. Now that we know what Andromeda is, the next question arrives quietly, like a whisper in the dark. What is it made of? Not the myth, not the name, the actual substance. The bones and breath of a galaxy spinning 2.5 million light years away. If you could hold Andromeda in your hand, if you could shrink it down and feel its weight, what would you be holding? Stars. Yes. But how many? And what else? What fills the space between them? What keeps it all from flying apart? The answers are stranger than you might think. Let's start with the most obvious part, the stars. Andromeda contains roughly 1 trillion of them. That's a 1 followed by 12 zeros. 1,000 billion suns scattered across a disk of space so vast that light itself takes 220,000 years to cross from one edge to the other. To put that in perspective, if every star in Andromeda were a single grain of sand, you'd need all the beaches on Earth, every shoreline, every desert, every grain from every coast, and you'd still come up short. But here's what makes it even more astonishing. Despite holding 1 trillion stars, Andromeda is mostly empty. If you were to fly a spaceship straight through the galaxy, threading between those trillion suns, the chances of actually hitting a star would be nearly 0. The distances between them are incomprehensibly large. Scientists suggest that if you scaled Andromeda down so that each star was the size of a grain of sand, the average distance between grains would be about 4 miles. Imagine a desert where every grain of sand is separated by 4 miles of emptiness. That's a galaxy. That's Andromeda. It seems as though the universe is less interested in filling space and more interested in stretching it. So if most of Andromeda is emptiness, what gives it shape? What holds it together? The answer is gravity. And speed, and something we still don't fully understand. Andromeda is a spiral galaxy, much like our own Milky Way. It has a bright, dense core at its center where stars are packed more tightly together, swirling in orbits around a supermassive black hole. From that core spiral, arms extend outward like frozen rivers of light, curving through space in elegant arcs. These arms aren't solid. They're not fixed structures. They're waves of density regions where stars' gas and dust gather more thickly for a while before drifting apart again. It's like watching traffic on a highway. The cars move, but the traffic jam stays in place, fed by new cars arriving as old ones leave. The stars in Andromeda's spiral arms are moving at incredible speeds, hundreds of kilometers per second. And yet, from our perspective, the galaxy looks perfectly still. That's because of the distances involved. When something is 2.5 million light years away, even motion at breakneck speed appears frozen. It's as if time itself slows down across that much space. Andromeda's disk is about 220,000 light years wide, but only about 10,000 light years thick at the edges. If you were to look at it edge on, it would appear flat like a coin spinning slowly in the dark. But from above, it would look like a pinwheel with arms that spiral outward in a graceful, logarithmic curve. Why spiral? Why not circular? Scientists believe it has to do with the way galaxies rotate. The inner parts spin faster than the outer parts, creating a kind of cosmic drag that stretches the arms out over billions of years. It's the same principle that makes water swirl down a drain or cream curl through coffee. Gravity pulls inward, momentum carries outward, and somewhere in the balance between those two forces, spirals emerge. But here's where things get strange. When astronomers measured how fast Andromeda's outer stars were moving, they found something unexpected. Those stars were moving too fast. According to the laws of gravity, they should have been flung out into space long ago. The visible matter in the galaxy, the stars, the gas, the dust, wasn't heavy enough to hold them in place, and yet they stayed, orbiting steadily as if held by invisible hands. The only explanation was that there had to be more mass, much more. Mass that we couldn't see. Mass that didn't emit light, didn't absorb light, didn't interact with anything except through gravity. They called it dark matter, and it turns out it makes up about 90% of Andromeda's total mass. Think about that for a moment. 90% of what Andromeda is, we cannot see. We can measure its effects. We can map its presence by watching how visible matter moves, but we cannot touch it, cannot photograph it, cannot point a telescope at it and say, there, that's where it is. It's like trying to study wind by watching leaves. You never see the wind itself. You only see what it does. So, when we talk about Andromeda, when we describe its trillion stars and spiral arms and glowing core, we're really only describing 10% of what's actually there. The rest is shadow. The rest is mystery. The rest is mass without form, holding everything together in silence. It's humbling, and maybe a little unsettling, because it means that most of reality is invisible. Most of what exists we walk right through without noticing. But let's return to the part we can see, the stars, the light, the substance of Andromeda that reaches us across the dark. Not all stars in Andromeda are the same. Some are young and blue, burning hot and fast, living only a few million years before exploding in supernovae. Others are old and red cool and dim, slowly fading over billions of years. Most are somewhere in between yellow, orange, white, each one a sun in its own right, each one potentially surrounded by planets we'll never see. Research shows that star formation is still happening in Andromeda, especially in the spiral arms, where gas and dust are dense enough to collapse under their own gravity. In those regions, new stars are being born, even now, as we speak, as you listen to these words. Light that will one day reach Earth is just beginning its journey, kindled in clouds of hydrogen 2.5 million light years away. And some stars are dying, exploding, collapsing, releasing their atoms back into the void, where they'll drift for eons before gathering again into something new. Andromeda is not a static thing. It's breathing, cycling, renewing itself over timescales so long that human civilizations rise and fall in the blink of an eye by comparison. It seems as though galaxies like living things are born, grow, and eventually fade. But the process is so slow, so gradual that we can only catch glimpses of it, snapshots frozen across billions of years. Another strange fact, Andromeda has 2 smaller companion galaxies orbiting around it, like moons around a planet. They're called M32 and M110, and they're dwarf elliptical galaxies, much smaller, much dimmer, but still massive enough to hold billions of stars. These companions are tidally locked to Andromeda, slowly being pulled apart by its gravity. Over time, they'll be torn to shreds, their stars absorbed into the larger galaxy. It's a slow kind of cannibalism, a quiet consumption that takes billions of years, but is in the end inevitable. Andromeda has done this before. Scientists have found faint streams of stars scattered around the galaxy's outer edges, the remnants of smaller galaxies that were devoured long ago. These streams are like cosmic fossils, evidence of ancient collisions, mergers, meals eaten in the distant past. It's as if Andromeda is built from the bones of smaller worlds. And here's the unsettling part. The Milky Way is doing the same thing. We're currently in the process of absorbing several dwarf galaxies, including one called the Sagittarius Dwarf Elliptical Galaxy, which is being stretched into long ribbons of stars as it spirals into our own. Galaxies grow by eating each other. It's not violent in the way we usually think of violence. No explosions, no crashes, no fire. Just gravity. Just the slow, patient pull of mass toward mass, star by star, over billions of years. And one day Andromeda will do the same to us, but we'll return to that collision later. For now, let's sit with the anatomy of Andromeda as it is today. A spiral galaxy, a trillion stars, a massive black hole at the center, spiral arms curving outward in frozen waves, 90% dark matter holding it all together, companion galaxies slowly being torn apart, star formation in the arms, star death in the core, a constant quiet cycle of birth and decay. If Andromeda were a city, it would be the largest city in the universe, and every star would be a house, and the space between houses would be desert stretching for millions of miles, and most of the city would be invisible, held together by something you could feel but never see. It's beautiful and strange, and almost too large to hold in your mind all at once. So maybe we don't need to hold it all. Maybe it's enough just to know that it's there, spinning quietly in the dark, made of light and shadow, visible and invisible, real and unknowable. Most of what we are we cannot see. Most of what holds us together is invisible. And maybe Andromeda is just showing us what we already know deep down about ourselves. We are more than what we seem, more than what we measure, more than what we can touch. And the spaces between us, the emptiness, the silence, the dark, that's not absence. That's part of the structure too. Have you ever felt like there's more to you than what people see? More weight than what shows up on the surface? Maybe that's what Andromeda teaches us. That substance and shadow are inseparable, that the invisible is just as real as the visible. That emptiness is just another kind of fullness. And now, as we drift further, we'll follow the light itself, the light that's been traveling for 2.5 million years just to reach your eyes. There's something strange about looking at Andromeda, something most people don't think about when they see that soft smudge of light in the autumn sky. You're not seeing it as it is, you're seeing it as it was, 2.5 million years ago. The light reaching your eyes tonight left Andromeda before humans learned to speak, before we made tools, before we buried our dead or painted on cave walls or wondered what the stars were for. That light has been traveling through the void alone and silent for longer than our species has existed. And tonight, it finally arrives. At your eyes. At this moment. What does it mean to see the past? Not a photograph. Not a memory. But the actual past delivered in photons still warm from a fire that burned when the world was young. Let's walk through that journey, slowly, the way light moves, the way time bends around distance. Imagine a single photon of light, born in the core of a star somewhere in Andromeda. It's created in a fusion reaction deep in the heart of a sun, where hydrogen atoms are crushed together under immense pressure and heat-releasing energy in the form of light. That photon doesn't leave the star immediately. It bounces around inside for thousands of years, ricocheting off other particles, slowly working its way outward through layers of plasma and gas. But eventually, it reaches the surface, and then it's free. It shoots out into space at the speed of light, 299,792 kilometers per second. Fast enough to circle the Earth 7.5 times in 1 second. Fast enough that if you could ride a beam of light, you'd reach the moon in just over a second, the sun in 8 minutes, and the edge of the solar system in about 5.5 hours. But Andromeda is not in our solar system. It's not even in our galactic neighborhood. It's 2.5 million light years away. And so, that photon moving at the fastest speed anything in the universe can move begins a journey that will take 2.5 million years to complete. Think about what that means. That photon leaves Andromeda at a time when Earth is in the middle of the Pleistocene epoch. Ice ages come and go. Glaciers advance and retreat. The climate shifts, cools, warms, cools again. And in East Africa, something new begins to stir. A species called Homo habilis, early humans. Not quite us, but close. They walk upright. They use simple stone tools. They scavenge. They hunt. They begin to think in ways their ancestors never did. That photon is still traveling, still crossing the dark, still moving at the speed of light, untouched, undisturbed, aimed at a small blue planet it doesn't know exists yet. By the time the photon reaches the halfway point of its journey, Homo habilis has given way to Homo erectus, then Homo heidelbergensis, then Neanderthals, and finally, sometime around 300,000 years ago, Homo sapiens, us, modern humans. We appear in the fossil record tentative and fragile, still learning how to survive. The photon keeps moving. It doesn't slow down. It doesn't stop. It just travels straight and true through the emptiness between galaxies. And on Earth, humans spread. We migrate out of Africa into Europe, into Asia. We learn to make fire, to sew clothing, to build shelters. We develop language. We create art. We bury our dead with flowers and ochre, as if death were something that deserved beauty. The photon is still traveling. Civilizations rise. The Sumerians build the first cities. The Egyptians build the pyramids. The Greeks philosophize. The Romans conquer. Empires expand and collapse. Religions are born. Wars are fought. Libraries are burned. Knowledge is lost and found and lost again. And through it all, that photon keeps moving. Silent, patient, aimed at a moment it cannot predict. By the time it finally reaches Earth's atmosphere, humans have invented the telescope. We've mapped the stars. We've named the constellations. We've begun to understand just barely what we're looking at when we look up. And then, on a clear autumn night, that photon enters your eye. It strikes the retina. It triggers a chemical reaction in the cells. They are sending a signal to your brain. And for the first time in 2.5 million years, that photon's journey ends. You see Andromeda, not as it is, as it was, when the world was ice and stone and our ancestors were just beginning to dream. It's a strange kind of time travel. You're not moving through time. Time is moving through you. The past is arriving constantly in the form of light. Scientists call this the look-back time. The farther away something is, the further back in time you're seeing it. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star, Alpha Centauri, you're seeing it as it was 4 years ago. When you look at Andromeda, you're seeing it as it was 2.5 million years ago. And here's the strange part. You can never see the present. Not in the cosmos. By the time light reaches you, the moment it depicts is already gone. The universe you see is always a memory. It's as if the present doesn't exist. Only the past endlessly arriving. But there's another layer to this story. Another twist in the way light behaves across such vast distances. Most galaxies in the universe are moving away from us. The universe is expanding, and as it expands, the light from distant galaxies gets stretched out, shifted toward the red end of the spectrum. Astronomers call this redshift. It's how we know the universe is getting bigger. It's how we measure distance. But Andromeda is different. Andromeda's light is blue shifted. It's compressed, squeezed toward the blue end of the spectrum. And that means only one thing: Andromeda is not moving away from us. It's moving toward us at a speed of about 110 kilometers per second. That's about 250,000 miles per hour, fast enough to cross the distance from Earth to the Moon in less than an hour. Andromeda is falling toward the Milky Way, and there's nothing that can stop it. This is unusual. Most galaxies are fleeing from each other, carried apart by the expansion of space itself. But Andromeda and the Milky Way are close enough that gravity has taken over. The mutual pull between the two galaxies is stronger than the expansion of the universe. And so, slowly, inevitably, we're being drawn together. It's like watching two rivers flow toward each other. You know they're going to meet. You know they're going to merge. You just don't know what the new river will look like when it's done. But here's the paradox. Even though Andromeda is moving toward us, the light we see is still old, still from the past. We're not seeing Andromeda as it is now speeding toward us. We're seeing it as it was 2.5 million years ago, when it was slightly farther away than it is today. By the time that light reaches us, Andromeda has already moved closer. The photons are chasing a galaxy that's no longer where they think it is. It's like sending a letter to someone who's walking toward you. By the time they receive it, they're already closer than they were when you sent it. The message is late. The information is outdated. the present has already changed. This is the nature of cosmic observation. We're always looking at ghosts, always seeing things that are no longer quite true. And yet, there's something beautiful about it. Because it means the universe has memory. Every photon is a record. Every glimmer of light is a piece of history delivered across the dark. When you look at Andromeda, you're not just seeing a galaxy, you're seeing a time capsule, a snapshot of what was, a moment frozen in light, carried across 2.5 million years of emptiness just to reach you. And that moment is real. It happened. Those stars were burning. That galaxy was spinning. That light was born. And now, after all this time, it's finally here. Research shows that light doesn't age. A photon emitted 2.5 million years ago is identical to a photon emitted 1 second ago. It doesn't decay. It doesn't fade. It just travels forever young until it hits something. And when it hits your eye, it's as fresh as the day it was born, the past arriving in the present unchanged. It's as if the universe refuses to let go of its history, as if every moment that ever happened is still out there somewhere, traveling through the dark, waiting to be seen. Have you ever thought about what it means to see something that no longer exists? Not in the way we usually think of memory, vague, distorted, filtered through emotion, but literal, exact. A perfect record of something that was. That's what light gives us. Not imagination, not reconstruction, just the past delivered whole. And here's the strangest part of all. Right now, at this very moment, light is leaving Earth and beginning its own journey toward Andromeda. Light from our cities, our fires, our screens. And in 2.5 million years, if anyone is there to see it, they'll look at that light and see us. Not as we are, as we were, right now, this moment. We're sending our past into the future, and the future is sending its past to us. It's a strange kind of conversation, slow, patient, carried across distances so large that by the time the message arrives, everything has changed. But the message still matters, because it's proof that we were here, that we existed, that once long ago there was a small blue planet orbiting a yellow star. And on that planet, someone looked up and wondered what the soft smudge of light could be. And the answer is traveling toward them now, slowly, silently, at the speed of light. 2.5 million years from now, someone in Andromeda might see us, might wonder who we were, might ask the same questions we're asking now, and the light will answer, the way it always does, with the truth, with the past, with a memory that refuses to fade. So when you look up and see Andromeda, remember, you're not just looking at a galaxy, you're looking at time itself, folded, stretched, delivered in photons. You're seeing what was, and in 2.5 million years, someone else will see what is. And the light will keep traveling, carrying the past forward, carrying the present backward, until everything that ever was has been seen by someone somewhere in the quiet dark. And now, as we stand at this edge of time and distance, we turn towards something even stranger. The collision that's coming slow and silent, written in gravity. In 4.5 billion years, the sky will change. Not slowly, not subtly, completely. The soft smudge of Andromeda that you see now, barely visible on autumn nights, will grow larger, brighter, closer, until one day it won't be a smudge anymore. It will fill the entire sky. A river of stars flowing overhead so vast, you won't be able to see where it ends. And then quietly, without thunder, without warning, it will pass through us. Andromeda is going to collide with the Milky Way. Not might, will. The math is certain. The trajectory is clear. And there's nothing in the universe that can stop it. But here's the strange part. When people hear the word collision, they imagine destruction, explosions, fire, the end of everything. That's not what's going to happen. When two galaxies collide, almost nothing actually hits. The stars are so far apart that they pass through each other like ghosts. like two clouds drifting through the same space, mingling, but not crashing. It's one of the most violent events in the universe, and also one of the gentlest. Let's walk through it, slowly, the way it will actually unfold. Right now, Andromeda is about 2.5 million light years away, and it's moving toward us at roughly 110 kilometers per second. That might sound fast, but on cosmic scales, it's a crawl. At that speed, it will take about 4.5 billion years for Andromeda to reach us. By the time it arrives, Earth will be a very different place. The sun will be older, hotter, brighter. Oceans may have boiled away. Life, if it still exists, will have moved underground or left the planet entirely. Humanity, if we're still around, will be unrecognizable. But let's imagine for a moment that someone is still here, still watching, still looking up. What will they see? At first, nothing unusual. For millions of years, Andromeda will just appear slightly larger in the sky, a little brighter, a little closer. But the change will be so gradual that no single generation will notice. Then, about 1 billion years before the collision, something shifts. Andromeda begins to dominate the night sky. It's no longer a faint smudge. It's a river of light stretching across the heavens, brighter than the Milky Way's own band of stars. By the time we're 500 million years from impact, Andromeda will look like a second Milky Way hanging overhead. Two galaxies visible at the same time, spiraling toward each other like dancers about to embrace. And then, the first pass. Andromeda doesn't hit us head-on. Galaxies rarely do. Instead, they graze each other like two spinning tops brushing past on a table. The outer edges of both galaxies begin to interact. Stars on the far reaches of each spiral start to feel the pull of the other's gravity. Some stars are flung outward, ejected into intergalactic space, becoming wanderers with no galaxy to call home. Others are pulled inward, drawn toward the centers of the merging galaxies. But most stars just keep orbiting. Their paths shift. Their trajectories change. But they don't collide. They don't explode. They just drift into new orbits, pulled by new forces in a dance choreographed by gravity. Research shows that during a galactic collision, the chance of two stars actually hitting each other is astronomically small. If you were standing on a planet orbiting a star in either galaxy, you'd see the sky fill with unfamiliar constellations, but you'd never see a star crash into your sun. It's as if the universe designed galaxies to pass through each other without touching. After the first pass, the two galaxies don't merge immediately. They move apart again, pulled by their own momentum. For a few 100 million years, they drift away from each other like two people who almost embraced but missed. But gravity doesn't let go. Slowly, inevitably, the two galaxies are drawn back together. And this time, the collision is deeper, more intimate. The spiral arms of both galaxies begin to distort. They stretch. They warp. They lose their elegant curves and become chaotic, tangled, pulled into long streams of stars that arc through space like ribbons caught in a storm. This is when something beautiful happens. The collision compresses clouds of gas and dust in both galaxies, triggering an explosion of star formation. Millions of new stars are born in a matter of a few million years. It's called a starburst event, and it lights up the merged galaxies like fireworks. If anyone is still watching from Earth, the sky will be ablaze with a new light. Blue-white stars, young and hot, scattered across the heavens. A sky brighter than any human has ever seen. But this brightness comes at a cost. Starburst events use up a galaxy's reserves of gas and dust very quickly. After the burst fades, star formation slows. Eventually it stops. The galaxy becomes quiet, old, filled with red and yellow stars that will burn for trillions of years, but with no new stars being born. It's like watching a firework, brilliant, brief, and then silence. By this point, the two galaxies have passed through each other multiple times. Maybe 3 times, maybe 4. Each pass pulls them closer together until finally they no longer have the momentum to escape. They settle, they merge, they become one. And when it's over, the new galaxy won't be a spiral anymore. It will be an elliptical galaxy, a smooth, featureless ball of stars with no spiral arms, no disk, no clear structure. Just a diffuse glow fading slowly into the dark. Astronomers have already given this future galaxy a name. Some call it Milkomeda, others call it Milkdromeda. Neither name has been officially adopted yet, but both capture the same idea: two galaxies once separate, now fused into something new. And somewhere in that new galaxy, our sun will still be orbiting, changed, moved, relocated to a different part of the galaxy, but still there, still burning. Scientists suggest that our solar system will likely survive the merger. The sun is far enough from the galactic centers that it will probably avoid the most chaotic regions. It will be nudged into a new orbit, perhaps farther from the center, perhaps closer, but it won't be destroyed. Earth, however, may not be so lucky. Not because of the collision, but because of the sun. By the time the merger happens, the sun will have swollen into a red giant, expanding so much that it may engulf the inner planets entirely. Earth might be gone long before Andromeda arrives. But even if Earth survives, even if it's pushed into a farther orbit where it can escape the sun's expansion, it will be a cold, dark world. No oceans, no atmosphere. Just a frozen rock drifting through a galaxy that no longer looks like home. And yet, there's something strangely comforting about the collision, because it means the universe doesn't end with loneliness. It ends with connection. Two galaxies falling toward each other, merging, becoming something new. It's as if, even in the vastness of space, nothing stays alone forever. Here's another strange fact. This isn't the first time the Milky Way has collided with another galaxy. It's happened before, many times. The Milky Way is built from the remnants of smaller galaxies that merged with it over billions of years. And Andromeda is the same. It's a patchwork. A collection of older galaxies that collided, merged, and became one. The streams of stars we see around Andromeda's outer edges are evidence of this. They're the ghosts of galaxies that were absorbed long ago. Galaxies don't grow by staying still. They grow by consuming, by merging, by becoming more than they were. It seems as though the universe prefers connection over isolation, prefers merging over separation, as if the natural state of things is not to drift apart, but to come together. And maybe that's the real lesson of the Andromeda collision. Not that everything ends, but that everything changes, that separation is temporary, that even across millions of light years, even across billions of years, things that were once apart will eventually find each other again. The collision won't happen in our lifetime. It won't happen in the lifetime of our species. It might not even happen in the lifetime of Earth itself, but it will happen. The trajectory is set. The mathematics is clear. And when it does, two rivers of stars will flow together, becoming one. Some people find this idea frightening. The thought that our galaxy, our home, will one day be unrecognizable, that the sky we know will be replaced by something strange and new. But maybe it's not frightening. Maybe it's just change. And change, even on cosmic scales, isn't the same as ending. It's just transformation, becoming something else, something different, something we can't yet imagine. Have you ever felt like you were drifting towards something inevitable, something you couldn't stop, couldn't change, but knew was coming? Maybe that's what Andromeda teaches us, that some things are written in gravity, that some meetings are unavoidable, that some endings are also beginnings. And when the two galaxies finally merge, when the spiral arms are gone, and the new elliptical galaxy settles into its final shape, the stars will still be there, still burning, still shining, just in a different sky, under a different name, in a different home. And maybe that's enough. Maybe it's okay that things don't stay the same, that galaxies collide, that rivers merge, that even the sky changes, because in the end, nothing is lost. It's just rearranged, redistributed, made into something new. The collision is coming, slow and silent, written in the pull of gravity. And when it happens, it will be the most beautiful catastrophe the universe has ever seen. But before we reach that distant future, we need to look at what's already here, hidden at the center of Andromeda, pulling everything toward it with a force nothing can escape. At the center of Andromeda, there is a place where light goes to die. Not slowly, not peacefully. It falls, it spirals. It crosses a boundary from which nothing, not even light itself, can return. And on the other side of that boundary, there is only silence, only darkness, only a gravitational pull so strong that space itself bends, curves, collapses inward like a wound that will never heal. At the heart of Andromeda, there is a black hole, not a small one, not a quiet one. A supermassive black hole weighing as much as 100 to 200 million suns. And it's not alone. Let's begin with what we know. And then slowly we'll drift into what we don't. Every large galaxy has a supermassive black hole at its center. It's not optional, it's structural. Scientists believe that black holes and galaxies grow together, feeding off each other, shaping each other, locked in a relationship that's been going on for billions of years. In the Milky Way, our black hole is called Sagittarius A star. It weighs about 4 million solar masses, 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. It's massive, but compared to Andromeda's black hole, it's small, almost modest. Andromeda's black hole is 50 times more massive, maybe more. The exact number is hard to measure because black holes don't emit light. They don't reflect light. They don't even let light escape. All we can do is watch the stars around them and calculate the mass needed to make those stars move the way they do. And when astronomers did that calculation for Andromeda, they found something strange, something that didn't make sense. In 2005, observations from the Hubble Space Telescope revealed that Andromeda's core isn't quite what it should be. Instead of one bright central point, there are two clusters of blue stars orbiting close to each other, both moving at incredible speeds. Scientists call this the double nucleus problem, and for years, no one knew what it meant. One hypothesis is that Andromeda doesn't have one supermassive black hole. It has two black holes orbiting each other at the center of the galaxy, locked in a slow, spiraling dance that will eventually end in a collision. If that's true, it would explain the double nucleus. Each black hole would be surrounded by a disk of stars, creating two bright regions instead of one. But there's another possibility. Maybe there's only one black hole, and the second bright cluster is just an illusion. A disk of stars tilted at an angle, creating the appearance of two centers, when there's really only one. Research is still ongoing. Observations are still being made. And until we get closer, until we can measure the gravitational waves or map the orbits more precisely, we won't know for sure. But either way, the truth is the same. At the center of Andromeda, there is a darkness that pulls everything toward it, a weight that cannot be seen but can always be felt. Black holes are often misunderstood. People imagine them as cosmic vacuums sucking up everything around them, devouring stars and planets like hungry mouths. That's not quite right. Black holes don't suck, they pull. The way gravity always pulls. The way the Earth pulls you toward its center. The way the Sun pulls the planets into orbit. The difference is the strength of that pull. Near a black hole, gravity is so intense that it warps space itself. Time slows down. Light bends. And if you get close enough, if you cross the boundary called the event horizon, there's no coming back. Not because the black hole is pulling harder once you're inside, but because space itself is curved so steeply that all paths lead inward. There's no direction you can travel that leads out. Every direction, even straight up, leads down. It's as if the universe has a trap door, and once you fall through the door, closes behind you. But here's the strange part. From the outside, you'd never see someone cross the event horizon. To you, they'd appear to slow down, moving slower and slower as they approached, until eventually they froze in place. Suspended forever at the edge, their light stretched out and dimmed until they faded from view entirely. But from their perspective, they'd cross the boundary in seconds. They'd fall. And on the other side, they'd find, well, no one knows. Because no information can escape a black hole. Whatever happens inside stays inside. It's the universe's most perfect secret. Andromeda's black hole isn't eating right now. It's quiet, dormant. Most of the gas and dust near the center has already been consumed or blown away, and there's not much left to feed on. But it wasn't always this way. Billions of years ago, when Andromeda was younger, the black hole at its center was active. It pulled in massive amounts of matter, heating it to millions of degrees as it spiraled inward, creating a glowing accretion disk that outshone the entire galaxy. These active black holes are called quasars, and they're some of the brightest objects in the universe. So bright that we can see them from billions of light years away, shining across most of cosmic history. Andromeda's black hole was once a quasar, but now it's quiet, sleeping, waiting. When the Milky Way and Andromeda collide, that will change. The merger will send shockwaves of gas and dust spiraling into both galactic centers, feeding both black holes, waking them up. And when that happens, the two black holes will begin to orbit each other slowly, at first, then faster and faster, until finally, in a cataclysmic event that will send ripples through the fabric of space itself, they'll merge. That collision will release more energy in a single second than all the stars in the universe produce in a year. It will create gravitational waves so powerful that they'll distort space-time across millions of light years. But we won't be there to see it, not directly. It will happen billions of years from now, long after Earth has gone cold, long after the sun has faded. Still somewhere, something will feel it. Some distant galaxy, some future civilization, some instrument we can't yet imagine will detect the ripples and know that two black holes, once separate, once distant, became one. And the new black hole will be even more massive, even darker, even quieter. But let's step back. Let's talk about what Andromeda's black hole has already done. Because black holes don't just sit at the center of galaxies, they shape them. They sculpt them. They control the flow of gas, the formation of stars, the structure of the spiral arms. Scientists suggest that the supermassive black hole at a galaxy's center acts like a thermostat. When it's active, it heats up the surrounding gas, preventing it from cooling and collapsing into new stars. When it's quiet, star formation picks up again. This feedback loop between black hole and galaxy is one of the reasons galaxies look the way they do. Without the black hole, galaxies would collapse into dense, chaotic balls of stars. With the black hole, they stay balanced, structured, ordered. It's as if the darkness at the center is what holds the light together. And then there's the history written in the stars around Andromeda's core. Faint streams of stars stretched out like ribbons arcing through space in long, looping orbits. These are tidal streams. The remnants of smaller galaxies that Andromeda consumed long ago. When a small galaxy gets too close to a larger one, the larger galaxy's gravity pulls it apart, star by star, stretching it into a long stream that eventually gets absorbed into the larger galaxy's structure. Andromeda has done this many times. There are at least a dozen tidal streams scattered around its edges, each one a fossil of a galaxy that no longer exists. It's a kind of cannibalism, quiet, slow, inevitable. The larger galaxy doesn't hunt, it just waits. And when something drifts too close, gravity does the rest. The Milky Way is doing the same thing. Right now, we're in the process of absorbing several smaller galaxies, including the Sagittarius dwarf elliptical galaxy. In a few 100 million years, it will be gone entirely, its stars scattered throughout our own. Galaxies grow by eating each other, and at the center of every meal, there's a black hole growing larger, growing darker, pulling everything inward. It's not cruel, it's not evil, it's just gravity. Just the way mass moves through space, following the curves, falling toward the deepest wells. But still, there's something unsettling about it. The idea that at the heart of beauty there's darkness, that at the center of every galaxy there's a place where nothing can escape. Maybe that's what makes black holes so compelling. They're not just objects, they're metaphors, boundaries, edges of the knowable, places where the rules break down and the universe says no further. You can study them, you can measure them, you can watch the way they bend light and warp time, but you can never go inside and come back to tell the story. They're the ultimate mystery, the final unknown. And Andromeda carries one at its heart, maybe two. Spinning quietly in the dark, holding 1 trillion stars in orbit, shaping the galaxy from the inside out. Have you ever felt like there's a part of you that no one can reach? A place so deep, so private that even you don't fully understand it? Maybe that's what black holes are, the universe's innermost self, the part that can't be explained, can't be lit, can't be seen. And maybe that's okay, maybe not. Everything needs to be understood. Maybe some things are meant to stay hidden, buried at the center, pulling everything toward them, without ever revealing what they are. Andromeda's black hole is one of those things. A weight, a silence, a gravity that holds the galaxy together, even as it consumes everything that falls too close. And when the collision comes, when Andromeda and the Milky Way merge, the two black holes will find each other. They'll orbit, they'll spiral inward, and they'll become one. A new darkness, a deeper silence, a heavier heart. And the stars will keep spinning around it the way they always have, the way they always will, held in place by something they can never escape. But even as we contemplate this darkness, this weight at the center, we need to remember that most of what holds Andromeda together isn't the black hole at all. It's something even stranger, something that fills the space around the galaxy like an invisible ocean. Imagine holding something you cannot see, cannot touch, cannot measure directly, but you know it's there because everything around it behaves as if it's real. That's dark matter, and it makes up 90% of Andromeda's mass. 90%, not 10, not half, 90. Which means when you look at Andromeda, when you see that soft glow of 1 trillion stars, you're only seeing 10% of what's actually there. The rest is invisible, silent, present only in the way it bends, space pulls, on light, holds galaxies together. It's like watching a puppet show and realizing that most of the performance is happening behind the curtain, in the hands of someone you'll never see. Let's start with the moment we realized something was wrong. Because for a long time, no one knew dark matter existed. We thought what we saw was all there was. Stars, gas, dust, light. That was the universe. And then in the 1970s, an astronomer named Vera Rubin looked at how galaxies rotate. She measured the speed of stars at the edges of spiral galaxies, expecting them to move slowly, because that's what the math said they should do. If a galaxy is just stars and gas, then the farther out you go from the center, the weaker the gravity and the slower the stars should move. Just like planets in our solar system. Mercury orbits fast, Neptune orbits slow. The farther from the sun, the slower the orbit. But that's not what Rubin found. She found that stars at the edges of galaxies were moving just as fast as stars near the center, sometimes faster, as if there was more mass out there than anyone could see. At first, people thought it was a mistake, a bad measurement, an error in the calculations. But Rubin checked, and checked again, and the numbers didn't change. The stars were moving too fast, and the only explanation was that there had to be more mass, much more. Mass that wasn't emitting light. Mass that was invisible. They called it dark matter. Not because it's evil or ominous, but because it doesn't interact with light. It doesn't emit. It doesn't absorb. It doesn't reflect. It's dark in the most literal sense. Invisible. And it's everywhere. In every galaxy. Around every cluster of galaxies. Filling the space between them like an ocean we can't see but can always feel. Scientists suggest that dark matter is a kind of scaffolding, a framework. The visible matter in the universe, stars, planets' gas dust, clings to it, follows its contours, settles into the valleys and ridges of its invisible structure. Without dark matter, galaxies wouldn't exist. The stars would fly apart. The gas would disperse. Everything we see would scatter into the void, untethered, lost. It's as if the universe we see is just foam on the surface of a much deeper ocean. In Andromeda, dark matter forms a massive halo around the galaxy, extending far beyond the visible disk of stars. This halo is roughly spherical, and it's so large that it reaches partway to the Milky Way. In fact, the dark matter halos of Andromeda and the Milky Way may already be touching, even though the galaxies themselves are still 2.5 million light-years apart. We're already connected, we just can't see it. The halo doesn't have sharp edges. It fades gradually as you move outward, becoming less dense but never quite disappearing. And because dark matter doesn't clump the way normal matter does, it spreads out smoothly, evenly, like a fog that fills every corner of space. When astronomers measure the rotation curve of Andromeda, how fast different parts of the galaxy are spinning, they find the same thing Vera Rubin found. The outer stars are moving too fast. And the only way to explain it is to assume that there's a massive halo of dark matter surrounding the galaxy, pulling on those stars, keeping them in orbit. Without that halo, Andromeda would tear itself apart. But here's the frustrating part. We still don't know what dark matter is. We know it's there. We can measure its effects. We can map its distribution. But we don't know what it's made of. It's not regular matter, not protons, neutrons, electrons, not atoms, not anything on the periodic table. It's something else, something that only interacts with the universe through gravity. Some scientists believe dark matter is made of particles called WIMPs, weakly interacting massive particles. These would be particles that have mass, but almost never interact with anything else. They'd pass through your body, through the Earth, through the Sun, without ever touching a single atom. Others think it might be axions, tiny, nearly massless particles that could fill space like a dense fog, collectively adding up to the enormous mass we observe. Still others wonder if dark matter is something stranger. Primordial black holes, extra dimensions, a modification of gravity itself. Maybe dark matter isn't matter at all. Maybe it's just a gap in our understanding of how gravity works at galactic scales. Research is ongoing. Experiments are being conducted deep underground in abandoned mines shielded from cosmic rays, trying to catch a single dark matter particle as it drifts through the Earth. So far, we've found nothing. No signal, no detection. No evidence beyond gravity. And yet, it must be there. Because without it, none of this works. Without dark matter, galaxies don't form. Stars don't cluster. The universe doesn't look the way it does. It's as if 90% of reality is hidden from us, and we're trying to understand the whole by studying the small fraction we can see. Think about that for a moment. Most of what exists we cannot perceive. Most of the universe is invisible. Not because it's far away, not because it's dim, but because it doesn't interact with light at all. We like to think we understand the world, that science has mapped reality, that we've uncovered the secrets of existence. But the truth is, we're barely scratching the surface. We're studying shadows and inferring shapes. It's humbling, and maybe a little unsettling, because it means that most of what's real we walk right through without noticing. We live inside it, we move through it, and we have no idea it's there. In Andromeda, the dark matter halo weighs about 10 times more than all the stars combined. That's 1 trillion stars holding 10 trillion solar masses worth of invisible matter around them. When you look at Andromeda, you're seeing the tip of an iceberg, the part that floats above the water. But the bulk of it, the mass that holds it all together, is submerged, hidden, known only by the way it displaces everything around it. And here's another strange fact. Dark matter doesn't clump the way stars do. Stars gather into galaxies because they collide, interact, lose energy, and settle into orbits. But dark matter doesn't collide. It doesn't lose energy. It just keeps moving, passing through itself, creating a smooth, diffuse halo that fills space like a ghost. If you could see dark matter, Andromeda wouldn't look like a spiral galaxy. It would look like a glowing sphere, faint and enormous, with the visible galaxy suspended in the center like a jewel in a cloud. It seems as though the universe prefers to hide its weight, to keep its mass invisible, to let us see only what's bright and leave the rest to mystery. But we're learning, slowly, piece by piece, using something called gravitational lensing. The way light bends around massive objects, astronomers can map the distribution of dark matter, even though they can't see it directly. When light from a distant galaxy passes near a cluster of galaxies, the gravity of that cluster bends, the light distorting the image like looking through warped glass. By studying those distortions, scientists can figure out how much mass is present and where it's concentrated. And every time they do this, they find the same thing: there's far more mass than visible matter can account for. The invisible ocean is always there. In some ways, dark matter is the most important substance in the universe. It's what holds galaxies together. It's what allows stars to form. It's what creates the structure. We see the clusters, the filaments, the cosmic web that stretches across billions of light years. Without dark matter, the universe would be empty. Just hydrogen and helium drifting apart forever, too diffuse to ever collapse into stars or galaxies or planets or life. We exist because dark matter exists, because it pulled the universe together, because it gave gravity something to work with, and yet we can't see it, can't touch it, can't even be sure what it is. It's the ultimate irony. The thing that makes everything possible is the thing we understand the least. Have you ever felt like there's more to the world than what you can see? More forces at work than what's visible on the surface? Maybe that's what dark matter teaches us. That reality is deeper than appearance. That weight doesn't always show itself. That the things holding everything together are often the things we overlook. In Andromeda, as in every galaxy, the visible is only a fraction of the real. The stars are beautiful. The light is mesmerizing. But the true substance, the true weight, the true structure that's hidden, silent, present only in the way everything else moves around it. And maybe that's the way it should be. Maybe the universe isn't meant to be fully seen. Maybe some things are designed to remain hidden, working quietly in the background, holding everything together without ever asking for recognition. Dark matter is the scaffolding, the foundation, the invisible hand that shapes galaxies and keeps them from flying apart. And Andromeda, with its trillion stars and spiral arms and glowing core, is just the part we're allowed to see. The part that light can touch. The part that reaches across 2.5 million light years to say, I'm here. But the rest, the 90% that stays in the dark, known only by its pull, by its weight, by the way it bends everything around it. It's as if the universe is a conversation where most of the words are whispered too quietly to hear, and we're left trying to understand the meaning from the few syllables that reach us. And yet, somehow, we keep listening, keep measuring, keep searching for the invisible ocean that holds everything afloat. Because even if we can't see it, we know it's there. We feel it. In the orbits of stars, in the curves of galaxies, in the way light bends around clusters of mass we'll never touch. Dark matter is real, even if it hides, even if it refuses to show itself, even if it exists only as a shadow cast by gravity alone. And now, after walking through invisible oceans and hidden mass, we return to something we can actually see, something simple, something human, something that's been waiting for you in the night sky all along. There's something extraordinary about Andromeda that most people never realize. Something simple, something quietly astonishing. You can see it right now. With your own eyes, no telescope, no binoculars, no equipment at all, just you, the night sky, and 2.5 million years of light arriving at your retina in a whisper. Andromeda is the farthest thing the human eye can see without help, the most distant object you'll ever perceive directly. And it's been there all along, waiting for you to look up. Let's talk about how to find it, how to see it, and what it means to touch something so far away with nothing but your vision. First, the science. Andromeda has an apparent magnitude of about positive 3.44. In astronomy, magnitude is how we measure brightness as seen from Earth. The lower the number, the brighter the object. The Sun is magnitude negative 27. The full moon is negative 13. The brightest star in the night sky, Sirius, is negative 1.46. Andromeda, at positive 3.44, is dim by comparison. But it's still bright enough to see with the naked eye if you know where to look and how to look. Here's the surprising part. Andromeda is actually larger in the sky than the full moon, about 6 times larger in fact. If your eyes could see all the faint light from its outer regions, it would appear as a glowing oval stretching across a significant portion of the sky. But we can't see all of it. We only see the brightest part, the core. The rest fades into the darkness, invisible to our eyes, blending with the black. So when you look at Andromeda, you're not seeing the whole galaxy. You're seeing a small, bright center surrounded by a vast halo of stars that your eyes simply can't detect. It's like looking at an iceberg and seeing only the tip. The best time to see Andromeda is autumn and early winter in the northern hemisphere. That's when the constellation Andromeda rises high in the sky, away from the interference of the horizon and city lights. If you live in the southern hemisphere, Andromeda is harder to see. It stays low on the northern horizon and is often obscured by atmospheric haze. But from latitudes above the equator, especially in North America, Europe, and Asia, it's one of the most accessible deep sky objects. The key is darkness. You need a clear night far from city lights. Light pollution washes out faint objects, and Andromeda is faint. If you're in a city, you won't see it. If you're in the suburbs, you might catch a glimpse. But if you're in a truly dark place, a rural field, a mountain, a desert, Andromeda will appear as a soft oval smudge, unmistakable once you know where to look. Here's how to find it. Start with the constellation Cassiopeia, which looks like a W or an M depending on the season. It's one of the most recognizable patterns in the northern sky. Once you've found Cassiopeia, trace an imaginary line from the middle star of the W down and to the right. You'll pass through a square of 4 stars. That's the constellation Andromeda. And just beyond that square, slightly to the left, you'll see it. A faint smudge, a soft glow, barely visible, but there. That's Andromeda, a galaxy, 2.5 million light years away, and you're seeing it with nothing but the 2 eyes you were born with. But here's where it gets tricky. If you look directly at Andromeda, it disappears, or at least it becomes much harder to see. This is because of the way our eyes work. The center of your retina is packed with cells called cones, which are great at detecting color and fine detail, but not very sensitive to dim light. The edges of your retina, however, are filled with cells called rods, which can't see color, but are extremely sensitive to faint light. When you look directly at something dim, you're using your cones, and they struggle. But when you look slightly to the side, you're using your rods, and suddenly the faint object becomes visible. Astronomers call this technique averted vision. You don't look at the object, you look near it. You let your peripheral vision do the work. It's counterintuitive. It feels wrong, but it works. If you stare directly at Andromeda, it fades. If you look just to the side, it brightens. It's as if the galaxy only reveals itself when you stop trying so hard to see it. This is one of the strange lessons Andromeda teaches us about perception. Sometimes the things we're searching for can only be found when we stop looking directly at them. When we soften our gaze, when we let go of the need to focus and instead just allow things to appear. Have you ever noticed that the harder you try to remember something, the more it slips away? But the moment you stop trying, it comes back. Maybe that's how the universe works too. Maybe some things are only visible when we stop forcing them into view. The first person to officially document Andromeda in writing was a Persian astronomer named Abd al-Rahman al-Sufi in the year 964 CE. He called it the Little Cloud and described it as a faint nebulous object visible to the naked eye on clear nights. But he wasn't the first to see it. People had been seeing Andromeda for as long as humans had been looking up. They just didn't write it down. They didn't know what it was. They just knew it was there. And that's part of the beauty. Andromeda has been watching us longer than we've been watching it. Every human who ever looked up on a clear autumn night saw that same smudge of light. Ancient Egyptians, Neolithic hunters, medieval monks, indigenous peoples across continents. All of them at some point saw Andromeda. They didn't know it was a galaxy. They didn't know it was made of stars. They didn't know it was moving toward us. But they saw it, and maybe some of them wondered what it was. Maybe some of them made up stories. Maybe some of them just felt a quiet sense of awe and moved on. Now we know what it is. But does that make it more or less mysterious? In some ways, knowing that Andromeda is a galaxy makes it more astonishing, because now when you see that soft glow, you're not just seeing a cloud or a star. You're seeing 1 trillion suns spinning in the dark 2.5 million light years away. You're seeing the past. You're seeing something so large it would take light 220,000 years to cross it. And you're seeing it with your own eyes. But in other ways, the mystery is gone. It's no longer a question, it's an answer. And answers, even beautiful ones, close doors that questions leave open. Maybe the best way to see Andromeda is with both, the knowledge and the wonder, the facts and the feeling, the science and the silence. If you've never seen Andromeda with your own eyes, I encourage you to try. Not because it's dramatic, it's not. It won't leap out at you. It won't dazzle you the way the moon does, but it will quietly, gently remind you that you're a part of something larger, that your eyes can reach across millions of light years, that the light touching your retina right now has been traveling since before humans existed. And if you have seen it, maybe it's time to look again. Because every time you see Andromeda, you're seeing it for the first time. The light is new. The moment is new. The galaxy has moved closer since the last time you looked, even if only by a few thousand miles. When you see Andromeda, take a moment. Let it settle. Let yourself feel the scale of what you're seeing. A galaxy. Visible, real, present. Not in a photograph, not on a screen, but there. In the sky, in your vision. Research shows that seeing celestial objects with the naked eye activates something different in the brain than seeing them through a telescope or in an image. There's a directness to it, an intimacy, a connection. Maybe it's because there's no glass between you and the light, no lens, no filter, just photons arriving from across the void, striking your eye, triggering cells that send signals to your brain that say, something is there. And something is. Something vast. Something ancient. Something that's been there all along, waiting for you to notice. The funny thing is, most people walk under Andromeda every autumn night and never see it. Not because it's hidden, but because they're not looking. Or they're looking at their phones. Or they're indoors. Or they've forgotten that the sky is still there, still full of things worth seeing. We live in a time when we can see galaxies billions of light years away through the Hubble Space Telescope. We can map the cosmic microwave background. We can detect gravitational waves from colliding black holes. But we've lost something too, the simple direct experience of looking up and seeing the universe with our own eyes. Andromeda is a reminder that we don't need technology to touch the cosmos. We just need darkness and patience and the willingness to look. It's there, right now, hanging in the autumn sky, waiting. And all you have to do is go outside, find a dark place, let your eyes adjust and look slightly to the side. It won't shout, it won't demand your attention, but it will be there. A soft smudge, a quiet glow. 1 trillion stars folded into a single point of light. And when you see it, you'll be doing what humans have done for thousands of years. You'll be reaching across space with nothing but your vision. You'll be touching something impossibly far away. And maybe just for a moment, you'll feel small. Not in a bad way, in a good way. In the way that reminds you that you're a part of something larger, that the universe is vast, and that you're standing in it looking out, seeing things that have been traveling toward you for longer than you've been alive. That's what Andromeda offers. Not answers, not certainty, just presence, just light, just the quiet reminder that the universe is still here, still spinning, still sending its light across the dark. And if you look, you'll see it. Not everything, not the whole galaxy, just a glimpse, just enough. Just enough to remember that the sky is deeper than it looks, that light travels farther than we can imagine, and that sometimes the most profound experiences are the simplest ones. You, the night, and a galaxy 2.5 million light years away finally arriving at your eyes. And now, as we stand beneath this ancient light, having walked through myth and science structure and shadow, we drift toward the end of this quiet journey. We've traveled a long way together tonight, through myth and measurement, through light and shadow, through distances so vast they bend the mind and mysteries so deep they might never be solved. We've walked beside a galaxy that's been watching us longer than we've existed, a river of stars flowing silently through the dark, carrying 1 trillion suns on a collision course with our own. And now, as we reach the end of this journey, there's one question left, one question that ties everything together. What does it mean to look at Andromeda? Not just to see it, but to really look at it, to understand what you're seeing, to hold in your mind the fact that the light touching your eyes right now left its source before humans had language, before we buried our dead, before we knew we were temporary. What does it mean to witness something like that? Maybe it means remembering how small we are, not in a diminishing way, in a grounding way, in a way that puts our worries, our fears, our daily struggles into perspective. When you look at Andromeda, your problems don't disappear, but they do shrink. They become part of a larger context, a context that includes galaxies and black holes and invisible oceans of dark matter, a context that stretches across billions of years and trillions of miles. And in that context, maybe the things we stress about don't seem quite as urgent. Maybe the arguments we have, the mistakes we make, the failures we fear, maybe they're not the catastrophes we thought they were. Because the universe keeps going, the stars keep burning, the galaxies keep spinning, and Andromeda keeps drifting closer, patient and unstoppable on a timeline so long that human lifetimes are barely a flicker. It's humbling. And maybe that's exactly what we need. But there's another side to it too. Because as small as we are, as brief as our lives are, we're still the ones asking the questions. We're still the ones looking up. We're still the ones trying to understand. And that's not nothing. That's extraordinary. Think about it. Out of all the things in the universe, rocks, gas clouds, black holes, empty space, only a tiny fraction of matter has organized itself in such a way that it can look back at the universe and wonder what it is. You are that matter. You are the universe looking at itself, asking questions, seeking answers, trying to make sense of the vastness. And Andromeda is part of that story. Because every time a human looks up and sees that soft smudge of light, every time someone asks, "What is that?" the universe becomes a little more aware of itself. We are the cosmos waking up. We are the way the universe experiences wonder. And maybe that's the real reason Andromeda matters. Not because it's big or beautiful or destined to collide with us, but because it reminds us that we are capable of caring about things that have nothing to do with our survival, things that are so far away they'll never affect us, things that exist purely for the sake of existing. We care about Andromeda because we can, because something in us is drawn to mystery, to scale, to questions without easy answers. That impulse, that curiosity, is what makes us human. It's what drove ancient astronomers to map the stars. It's what pushed Edwin Hubble to measure the distance to Andromeda and realize the universe was bigger than anyone imagined. It's what keeps scientists up at night, searching for dark matter, mapping tidal streams, calculating the trajectory of a collision that won't happen for 4.5 billion years. We don't need to know these things, but we want to. And that wanting is precious, sacred even. Because in a universe that seems indifferent to us, that moves on time scales we can't comprehend, that operates by laws we didn't invent and can't change, our curiosity is an act of defiance, a refusal to accept meaninglessness, a declaration that even if we're small, even if we're temporary, we matter. We matter because we notice, because we care, because we look up. And Andromeda, drifting silently through the dark, has been the recipient of that gaze for thousands of years, watched by people who didn't know what it was but knew it was important, studied by astronomers who gave their lives to understanding it, seen by you right now as you listen to these words. That connection between you and a galaxy 2.5 million light years away is real. It's made of light. It's made of attention. It's made of the simple fact that you're here listening, wondering, caring about something impossibly distant. And maybe that's the best definition of meaning we'll ever find. Not something handed down from the universe, but something we create. By looking, by wondering, by refusing to let the vastness silence us. Andromeda doesn't care if you see it. It doesn't need your attention. It doesn't know you exist, but you see it anyway. And that act of seeing, that act of caring, transforms both of you. You become someone who has looked across 2.5 million light years, and Andromeda becomes more than just a galaxy. It becomes a story, a connection, a reminder that we're part of something larger. Have you ever felt that? That strange, quiet thrill of realizing you're connected to something vast, that you're not separate from the universe but woven into it. That's what Andromeda offers. Not answers, not comfort, just presence. Just the reminder that you're here in this moment, part of a cosmos that's bigger and stranger and more beautiful than we'll ever fully understand. And as we close this journey, as we let the silence settle back in, I want you to remember something. Andromeda is still out there, still drifting closer, still spinning, still carrying its trillion stars on a path that was set in motion billions of years ago. And when you look up on a clear autumn night, when you find that soft smudge of light hanging above the horizon, you'll know what it is. You'll know its history, its structure, its destiny. But more than that, you'll know that you're seeing something real, something ancient, something that's been traveling toward you for longer than humans have existed. And maybe you'll feel a little less alone, because the universe isn't empty. It's full of light and shadow matter and mystery, questions and wonder. And you're part of it, not as an observer, as a participant, as someone who looks up and asks, "What is that?" As someone who cares enough to learn the answer. That's what Andromeda has given us tonight. Not just facts, not just science, but a reminder that curiosity is beautiful, that wonder is worth holding on to, that even in a universe this vast, this old, this indifferent, there's still room for meaning. We make that meaning by looking, by asking, by refusing to accept the darkness without at least trying to understand it. And so, as we drift toward the end, as the words fade and the silence returns, I want to leave you with this. Andromeda is still out there, waiting, not for you, but for anyone willing to look. And if you look, you'll see it. Not everything, not the full truth, just a glimpse, just enough. Just enough to remember that the universe is larger than you thought. That light travels farther than you imagined, and that you, small, temporary, fragile, are still capable of reaching across the void and touching something impossibly distant. That's the gift. That's the lesson. That's the quiet truth Andromeda has been carrying across 2.5 million light years just to reach you. You don't need to understand everything. You don't need to solve the mystery. You just need to look up. And when you do, the universe looks back, not with eyes, not with intention, but with light, with presence, with the simple fact that it's there, and so are you, and for a moment across the vastness, you're connected. Sleep well, dream gently, and the next time the sky is clear and the autumn night is dark, step outside. Look up. Find that soft smudge of light. And remember, you're seeing the past. You're seeing 1 trillion stars. You're seeing a galaxy that's falling toward us, slow and inevitable, like a river that never stops flowing. You're seeing Andromeda, our silent river of stars, and it's beautiful, and it's real, and it's been waiting for you all along. Thank you for walking this quiet journey with me, for listening, for caring, for giving your attention to something that's so far away, it almost doesn't seem real. But it is real, and so are you. And that connection between the distant and the present, between the vast and the small, that's what makes all of this matter. There are more stories waiting in the dark, more galaxies, more mysteries, more quiet journeys through science and wonder. And I hope you'll join me again when the night is still, when the world is quiet, when you're ready to drift through the cosmos, one soft fact at a time. Until then, rest, dream, and know that the stars are still there, still burning, still waiting for someone to look up and wonder. Good night.